Hello, Mr. Betts here. I want to talk about how we're going to start doing calculus with polar equations. In particular, I want to talk about how we're going to take derivatives with polar equations and what those derivatives are going to mean. So I'm going to give you a lot of information here, and then the example that I do is going to be a lot more useful in interpreting this stuff. Um, so the first one, there's actually four different derivatives and kind of a fifth here if we throw in a second derivative that we're going to look at with polar relations. So the first one will sometimes be written in prime form. So r prime of theta is just another way of saying d r d theta. And remember, r is the distance between a point and the origin. And so when we find d r d theta, we're finding how fast that distance between the point and the origin is changing. So this is a pretty straightforward derivative. If we have a function r equals something in terms of theta, we take the derivative just like we did with equations that was y in terms of x. If we want to find dx d theta or dy d theta, which are both kind of useful for motion problems. I shouldn't say kind of, they're very useful for motion problems. If we want to find one of those derivatives, we're going to take the r equation that we have and we're going to plug it in for r in these equations here. X equals r cosine of theta, y equals r sine of theta, and then we're going to take the derivative of that. So by plugging that in for r here, we're going to have x entirely in terms of theta. So now at that point, it's just a regular derivative. I'm putting regular in quotation marks, but we're just taking the derivative with respect to theta then. Same thing with y. If we plug the r function in for r here, then that's going to be entirely in terms of theta. Then we can use that to find dy d theta. If we want to find dy dx, remember dy dx is slope in the traditional xy coordinate plane. When we're talking about slope, we're talking about the xy coordinate plane. We're going to do this the exact same way we did it with parametric equations. The only difference is with parametric equations, we usually use t. With polar equations, now we're using theta as our parameter. So by writing the r function in terms, writing x and y in terms of theta, now we've created a system of parametric equations, and we find dy dx by dividing dy d theta by dx d theta. Also, coming from parametric equations, if we want a second derivative in the xy coordinate plane, then what we're going to do is the same as what we did with parametric equations. We take the first derivative. Remember, this is going to be in terms of theta. So when we take the derivative, when we're taking derivatives here, we're going to get derivatives in terms of theta. So we take the derivative of that in terms of theta, but since we want the second derivative with respect to x, then we have to divide by dx d theta. So this equation is the exact same equation we use for second derivatives with parametric equations, except that one had t's in here instead of thetas. So we're going to use these derivatives to answer questions about moving objects. Remember when I introduced polar equations, I mentioned that polar equations are often really good for certain motion problems. So if we have an object that's moving based on a polar equation, then these derivatives represent certain things. Generally, what we're going to say is that theta and t are somewhat interchangeable. So theta is increasing as time passes. So we can think of these derivatives as like dr dt, dx dt, dy dt. And so we're actually thinking about these the same way we thought about the parametric equations. So dr d theta, remember I mentioned, is telling us how fast r is changing. So if r is getting bigger or smaller, we're talking about whether something's moving toward the origin or away from the origin. I have an asterisk here because there's some kind of special cases there, and I'm going to talk about that in a moment. Dx d theta is talking about how fast the x-coordinate is changing. Since the x-coordinate tells us where the object is along the x-axis or horizontal location, then dx d theta is going to tell us whether the object is moving right or left. All right, so if dx d theta is positive, it's moving right. If dx d theta is negative, it's moving to the left. Dy d theta is similar to dx d theta, but we're talking about vertical motion, so up or down. Dy dx we are not going to use to interpret motion, and it's a common mistake to make, but dy dx is simply interpreted as the slope of a tangent line, and that's it. We can get some information about motion, but that information is going to be ambiguous because, for example, a positive slope, we don't know if the positive slope is because the object is moving up and to the right, or if the slope is positive because it's moving down and to the left. So we want to answer questions about motion with these derivatives, and we're going to leave dy dx for just slopes. So I mentioned there's some special cases with dr d theta. So I want to look at those in particular. I have the graph of a polar function here, and the green part of that graph is where r is positive. So I'm going to write this down here a second. Green means r is positive, and the red part is where r is negative. And so the motion of this object here is going to be generally in a counterclockwise direction. So I'm going to be thinking about the object going in this direction, but here it's going to be moving that way and moving that way and moving that way. So we're moving around following this path. So I want to look at each of these cases and look at a point on this graph and kind of talk about what that would mean. Remember, dr d theta is going to tell us whether we're moving toward or away from the origin. So I'm going to find a point here where r is positive and dr d theta is positive. And that's going to be, let's say this point right here. So r is positive because it's on the green part. So this distance right here, we're going to say is positive. And dr d theta here is positive because r is getting bigger. So as we're moving along, r is increasing and the object is moving away from the origin. So if both of these are positive, then we're going to have motion away from the origin. However, if r is positive and dr d theta is negative, that would be like this point right here. In this case, r is positive, but as the object moves, it's actually getting closer to the origin here. So this is going to be toward the origin. Now, when r is negative, that tends to be where it's a little trickier to think about. So I'm looking at points along that red part of the curve, and r is negative and dr d theta is positive. So remember, dr d theta is positive. This means that r is getting bigger. I shouldn't say bigger. Let's say r is increasing. Let's use some more precise language. Getting bigger could imply that the absolute value is getting bigger, and if r is negative, then that's ambiguous. So if r is increasing but r is negative, then the value of r, the absolute value of r, is actually getting smaller. So in this case, we're actually looking at a point right here where r is negative, but r is getting closer to 0 because r is increasing. So in this case, we are moving toward the origin again. And then the last example, you could probably guess what it is, but let's kind of talk through it here. If r is negative and dr d theta is also negative, then this means that r is decreasing. So if r is negative and decreasing, then the absolute value of r is actually getting bigger. So if it's negative and decreasing, it's becoming a bigger negative number, so it's moving away from the origin. So one easy way to think about this is if r and dr d theta have the same sign. So if they are the same, r is positive and dr d theta is positive, that means r is positive and getting bigger. Or if r is negative and dr d theta is negative, that means r is negative and it's decreasing. In both of those cases, it's moving away from the origin. And then if r and dr d theta have different signs, they're kind of competing against each other and it's moving toward the origin. So if r is positive and decreasing, it's moving toward the origin. Or if r is negative and increasing, it's also moving toward the origin. A couple other special cases with dr d theta. One, if r is 0, it doesn't matter what the derivative is here. If r is 0 and our object is moving, then no matter what, it has to be moving away from the origin. Because if r is 0, it's at the origin. So it's an important idea there. If r is 0, then it's at the origin. So if it moves at all in any direction, then it's moving away from the origin. Okay, the other one is if dr d theta is 0, that means that r is neither increasing nor decreasing. So if r is not getting bigger nor is it getting smaller, then distance from origin is not changing, or we could say constant. Now, to be clear, this could be happening at a moment, and a moment later, dr d theta is some other non-zero value. But at the moment where dr d theta is 0, it's neither getting closer to the origin nor is it getting further from the origin. So if we think about the motion here, as we travel along, I'm going to use the green part to start with. As we travel along here, we're moving away from the origin. We hit this point right here, and then we start moving toward the origin. So at that point right there where we change from moving away to moving toward, that's where dr d theta is going to be 0. All right, so not only at this point are we not getting closer or farther from the origin, but it's staying constant at that moment. That sounds kind of contradictory, but that's what we would say. It also is the place where it is the farthest from the origin. So when we change from moving away from the origin to toward the origin, it's going to be the farthest point from the origin. The other one here where we're moving away from the origin and then toward the origin, this is actually where dr d theta is negative changing to positive. In this case, we have another point here where dr d theta is going to be 0. So at that point, the object is neither moving away from the origin nor toward, but it's switching between the two. And that's it. Lots of information. Good luck.